is the gradient-based energy minimization. If you put all these together in such a way, it will mimic Jeff Gray's original docking protocol. So let's see how that works. So this whole thing is recapitulated in this protocol move, where first we do the low resolution docking, and we move into here, we repack the side chains and do a minimization, and then we do a high resolution refinement. That's my dock high. And then we also want to do accept or reject it, and we do it many, many times, and that's specified on the command line. And then we can do our clustering and predictions. So, so score versus RMSD should always create an energy funnel. So the lowest energy model should be closest to native structure, and that's pretty much the backbone Rosetta, how things work. As you can see, if I just do it once, if I do score versus RMSD, a script that has been provided to you, and I give it the native structure, and then I give it my my PDB file. If I look here, I can see that my scores are different, but my RMSDs are high. But I've only given it 2 files, and this again shows you why you want to do the many decoys, since they are Monte Carlo searches, not molecular dynamics. So we usually use on the order of 10,000 decoys in order to create an energy funnel. So if I just take my analysis results and put it in some molecular viewer, the low resolution found the native epitope, and I bet if we did this a couple more thousand times, we'd get even closer. Perhaps do more minimization and small docking perturbations here at the low resolution scale, or the high resolution scale rather, and we get closer to our epitope. So even with one structure, we do pretty good at finding the native epitope. It searched this whole thing. So when you analyze your results, you should see energy funnels. The native should be the lowest thing compared to RMSD. So these are taken from the Gray paper. As you can see, most of them create a energy funnel, and the lowest RMSD is indeed the native, closest to the native structure at least. So the lowest score is closest to the native structure when when an energy funnel exists. So let's quickly, I wanted to show you something actually, and this is something people have been emailing about, and you can email me about, and I'll show you how to set this up. But Rosetta is completely command line based so far, but it does have a graphical mode. So I can call on Rosetta scripts.graphics, and then I can give it the flags file with all that stuff I showed you, and then you can put this tag parser view, and when you run it, you actually get a sort of a crude view of what's happening. So this is low resolution mode, where we took off all the atoms and converted them to centroids, and it's walking along the energy landscape here. Since I randomized it, it starts here, and hopefully it'll move around and try to find a native structure, but perhaps not. When it gets done with the low resolution search, we'll do the high resolution refinement, so we can just let it go. There's generally not as many moves as this. I specified more moves to make the simulation go longer. You can make as many moves as you want. Still in low resolution mode. Okay, now we've repacked in the rotamers, and we're doing gradient-based minimization right now, where it does allow backbone movement, as you can see, and we're just trying to drive down that energy well. I think this is the minimization step. Yeah, it's the min mover we called on in our protocol file. Okay, and this is the high resolution dock. So it's gonna refine where exactly the interface is right here, and it's just going to do very small perturbations, unlike low resolution dock where we search the entire landscape. So that's kind of a cool way to view it, and it's a really nice debugging tool, especially if you're working with multi-complexes, to see if the right things are happening with your protein. A couple times you'll run into the wrong chains or jumping, and your protein falls apart. You don't really know why, and it's really easy to debug if you use the graphical viewer. So, and here's some of the resources, all these great docking papers. You'll see Jeff Gray's on pretty much all of them because he's the one who, his lab is very involved in Rosetta or protein-protein docking. I've also given a list of some of the servers I use. SnugDoc just does the comparative modeling Liz talked about of antibodies, and it does the docking move. So all you pretty much do is enter a FASTA file and you're good to go. Rosetta Docs is the automated docking. Rosetta Antibody is the automated antibody homology modeling server. So that's it. If there's any questions, feel free.